In this presentation, I want to introduce GoSafe, an algorithm for globally optimal safe robot learning. The field of machine learning has seen many exciting advances and developments in recent years. However, leveraging those successes for robot control is often not straightforward. One of the issues that we are facing is that many of the popular machine learning algorithms cannot provide guarantees during exploration and therefore may encounter failures during training, as in the video shown above. While for this particular robot, this is uncritical in general when dealing with more fragile robot hardware, failures may cause severe hardware damage or even risk the injury of people standing close by. And therefore, in general, if we want to use machine learning methods to optimize policies of robotic systems, we need to be able to provide safety guarantees. When using machine learning methods for robot control, we typically try to optimize the reward function that depends on policy parameters, and we also have constraints, and during all times we need to be able to guarantee that the constraint stays above some critical safety threshold. If we now consider reward function, constraint functions, and also robot dynamics to be unknown, this problem is unsolvable in general, and therefore we assume that an initial safe area is given. Under this assumption, the popular SAFEOPT algorithm can now find optimal policies while guaranteeing safety with high probability, and it does so by locally expanding in this initially given safe area. However, if we now assume that the functions continue such that there is an additional safe area with a new optimum, then SAFEOPT will not be able to find this new safe region since it is disconnected in parameter space and SAFEOPT cannot jump between safe regions. And therefore, SAFEOPT in this example will not be able to find the global optimum. There exist methods that can find the optimum also in disconnected safe regions while still providing guarantees, but they then require a model of the robot dynamics. And this is where GoSafe comes in. So GoSafe can find the optimum in disconnected safe regions without the need for a model and while guaranteeing safety with high probability. In more technical terms, we assume our robot to be governed by Lipschitz continuous dynamics and controlled by a parameterized policy. Our objective is to maximize an unknown reward function while not violating any constraints. We further have an immediate constraint function that depends on the current state of the system, and the constraint g is then basically the minimum over the immediate constraint function values encountered over the course of an experiment. We assume that we can measure the state of the robot and that we get noisy measurements of reward and constraint after each experiment. If we now have that reward and constraint are Lipschitz continuous, we can estimate both using Gaussian processes, and the GPs then also provide us with uncertainty bounds. SAFEOPT now leverages those bounds to compute a set of policy parameters that are safe with high probability, and by only sampling from the safe set during exploration, it can provide safety guarantees. GoSafe extends this idea from the pure parameter space to the joint initial condition and parameter space, and in addition also includes the strategy for a global search. And this I want to illustrate now in a graphical example. So let's assume that we want to optimize a single parameter for a system with a one-dimensional state. In this image, hatched areas are unsafe, while white areas are safe. A0, X0 marks the pair of initial condition and policy parameter that were given in the beginning and that we know is safe. Now, starting from there, GoSafe proceeds in 3 stages. In the first stage, we explore in the parameter space using SAFEOPT and find our first optimum marked with the blue cross. Next, we explore in the joint initial condition and parameter space, so we also try out different initial conditions, and that way find a new optimum. This optimum is now in a safe region, which is connected in the joint initial condition and parameter space, but disconnected in the pure parameter space, and therefore SAFEOPT in stage 1 was not able to find it. So that way, we can already improve upon pure SAFEOPT. But we can do even more. Now we are equipped with a set of safe policies and a set of initial conditions from which we can trigger those policies. That means we can now also explore globally. We can explore globally, observe the state of the system, and whenever we get too close to violating any constraint, we can trigger one of our safe backup policies. In that case, we then mark the experiment as failed, which is highlighted with the red crosses in this image. Following the strategy, we finally also find a new safe area, and once we found a new safe area, we can return to stages 1 and 2 and explore locally within this newly found safe region. Then we can do another round of global search and finally explore the whole space and find a global optimum, which here in this case is in the last safe region. Now I want to explain in some more detail how the global search strategy works and how we interrupt experiments. One of the main differences between SAFEOPT and GoSafe is that SAFEOPT assumes that once we apply policy parameters, we immediately get returned values of the reward function and the constraint without any possibility to intervene. In robotics, when we apply policy parameters, we first conduct an experiment and then get the values for the reward and constraint function. But throughout the experiment, we are able to observe the system state and also we are able to intervene. The top plot now shows the state of evolution over a successful experiment and also the immediate constraint function, which we must not violate, but which is also unknown. After stages 1 and 2, we now have a set of safe policies and a set of initial conditions from which we can trigger those policies. That way, we can now define a border of the set of safe initial conditions. And this tells us that as long as we are below this border, we can for all states trigger a safe backup policy and for which we can guarantee safety. As soon as we are above the threshold, we lose all our guarantees. Now we can explore globally and observe the state during the experiment. If we now hit the border of the set of safe initial conditions throughout the experiment, we can trigger a safe backup policy, mark the experiment as failed, and restore safety. Following this strategy then also allows us to provide theoretical guarantees. Under the assumptions of SAFEOPT extended also to the initial condition space, we can guarantee that the immediate constraint function is satisfied for all constraints, all times, and all experiments with probability at least 1 minus delta. And the proof proceeds as follows. So during stages 1 and 2, the safety guarantees follow straightforwardly from SAFEOPT, since this is basically what we are doing during these stages. During stage 3, we switch to a safe policy whenever we hit the border of the set of safe initial conditions. If we switch to a safe policy, safety follows again from the SAFEOPT policies. If we do not switch, that means we have never hit the border of the set of safe initial conditions, and then safety basically follows by definition of the set of safe initial conditions. We can also make statements about optimality. So under still the same assumptions, GoSafe converges to the optimum within the maximum safely reachable set with epsilon precision and probability at least 1 minus delta. For the proof, we first need to guarantee that we actually converge to this maximum safely reachable set. During stages 1 and 2, we only explore in the joint initial we locally explore in the joint initial condition and parameter space, and the convergence to the maximum connected safe set, so connected in the joint initial condition and parameter space, follows from SAFEOPT. Safe regions that are disconnected in the joint initial condition and parameter space we can find during stage 3. However, here we need to make a restriction. There may exist safe areas whose policy parameters impose a trajectory which would drive us outside of the set of safe initial conditions. In that case, we would trigger a safe backup policy and mark the experiment as failed, so we will not be able to find such regions. Therefore, such kind of regions are excluded from the maximum safely reachable set. Having defined the maximum safely reachable set in such a way, we can guarantee convergence to it by alternating stages 1 to 3, and then the convergence to the optimum within the safe set follows from SAFEOPT. Finally, we can make a statement about the global optimum. So if the global optimum is contained within the maximum safely reachable set, GoSafe will converge to it with epsilon precision and probability at least 1 minus delta. So far the theoretical guarantees. Now I want to show the algorithm in action. So we evaluated the algorithm on the Furuta pendulum, and the goal here was to find a balancing policy and to guarantee safety. That means we want to guarantee that the pendulum never drops, so that what we see in the video on the right never happens. For this, we also use the concept of a backup controller. So, like as in this video, when we notice that something is shaky, that something is moving too fast, we interrupt the experiment and trigger a safe backup policy to restore safety and make sure that the pole does not drop. So now we apply our algorithm. So first we do SAFEOPT and locally explore the initially given safe region. On the top right, we see that it should be posterior over the policy parameters, and in the bottom plot, we see the reward of both SAFEOPT and GoSafe, which do exactly the same during stage 1. After having explored the initial safe area with SAFEOPT, we then go to stage 2, exploring the joint initial condition and parameter space. which we want to join here, and then we go for the global search. So now we explore policy parameters that are potentially unsafe, and whenever we get too close to violating a constraint, we interrupt the experiment and trigger a safe backup policy. And as we can see, the poll actually never drops, so we are always safe. And finally, we can find a new safe region which is disconnected in parameter space, so a region that SAFEOPT would not have discovered. And now GoSafe can explore also this newly found safe region, and its reward increases even further, while the one of SAFEOPT is still stuck since it cannot do better than what it finds in the initially given safe region. And if we now directly compare the outcomes of SAFEOPT and GoSafe, we can see that the GoSafe policy yields a more steady behavior, while SAFEOPT is way more shaky. And also the reward of GoSafe is higher than that of SAFEOPT. So in conclusion, we have seen that GoSafe can learn global optima in situations where SAFEOPT would be stuck in a local one. Further, we have compared our algorithm to expected improvement with constraints, and this we can see in the top right plot. The top right plot basically tells us that the maximum reward found by GoSafe and by expected improvement with constraints is pretty much the same in the two runs. However, expected improvement with constraints committed 7 respectively 10 failures over the two runs, or in the two runs, while for GoSafe we never had any failures, so the pole of the pendulum never dropped. So in conclusion, GoSafe combines the best of both worlds, optimality and safety.